Alright, we are recording now, and we'll go from current slide, and we're starting with very few people. Sorry about that, but I'm glad y'all are here. And that's one slide past where we were supposed to start. Alright, so one more time, any questions, concerns, issues? Let me just make sure that we've got 5 people here so far. That's just enough for a basketball team. 1, 2, 3, 4, 5. That's all we got so far. So any questions? Alright, where we left off last time, we're in chapter 2, polynomial and rational function. Here comes somebody, but I can't see who it is because they're blocking him. There's Rosa here. Let me get Rosa marked here. Okay. Alrighty. Let's see if somebody else might be there. I think not. For some reason, I guess it's Zoom blocks people, blocks me being able to see who's coming in. It's some combination somewhere. It seems ludicrous that you're trying to let people in and yet it blackens out their name. So anyway, I think I've got all of you here that are here so far. Now we got enough for a volleyball team anyway. Okay, where we were in chapter 2, whoops, here's somebody else coming in. I can't see who it is. I think it's Anaya, but I can't see for sure. Well, it won't uncover her name, so let me try it down here. Oh, there she is. Yep, Anaya was coming in. Okay. Now we're up to 8 students, believe. Okay. All right. Make sure there's nobody else in the waiting room. Don't see anybody. No, we got 7 here. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 here. I'm the 8th one. Okay. It looks like maybe somebody else. No, I guess not. Okay. So let's minimize that and go on. Like I started to say a few times now, but somebody else comes in, which is good. We're in chapter 2, polynomial and rational functions. Yes, question? Okay. In section 2.2, polynomial functions of higher degree. 2.1 was dealing with quadratic functions, and 2.2 are functions of higher degree. We're on page 128, getting ready to start example 4. So let's hit it. Now that is not on the slideshow. In fact, 4 and 5, neither one of them are on the slideshow. So we'll be starting from the whiteboard. And I've got a little bit of housekeeping to do with it because it puts the taskbar, of course, in the middle of the white space, or not in the middle, but in the white space, so it gives me less white space to work with. All right, and I'll move the whiteboard as far as I can to the left and up, so I have maximum white space with which to work. Okay, no questions so far? All right. Example 4 on page 128. Sketch the graph of f of x is equal to 3x to the 4th minus 4x cubed. Now, says sketch the graph. It doesn't tell you anything else to do but sketching the graph. All right, now here's where I suggest that you start. Okay, draw something fairly close to a vertical line for the y-axis or the f-axis, and another horizontal line for the x-axis. Okay, tick off a few points. 1, 2, 3. Oh, here comes Janae. Let me get Janae in here and marked in the roll book. right. That gets us up to 3, 4, 5, 6, 7, 8 students. So we're coming closer. Wait, I thought we had that before. Let me see how many we got. Yeah, 8 students. Oh, here comes one more. Kanisha's here. Okay, let me get her marked. All right, 2, 4, 6, 7, 8, 9. And here's Weston. So let me get Weston marked. All right, broke double digits here, which is good. Hope some more are coming. So let me make sure that there's no one else in the waiting room. Nope, I don't see anybody. Yes, we did. Did you not get the invite? Oh, okay. Yeah, we had class on Tuesday. Now, I know some people had to deal with voting and things like that, so that's understandable, but it's all recorded out there on the YouTube videos. So it should be there. All right. So for those who have come in, we're in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree. 2.1 was Quadratic Functions, that's Degree 2. For those that are higher degree, 3 or higher, that's what we're dealing with here. And that's the example we're on now, example 4 on page 128, sketch the graph of this function. So we're just starting the process of setting up to graph it. So if I can get my pen to write properly, sometimes it does, sometimes it doesn't. I don't need that many ticks there, but I'll do a few on the other side too. I don't think I'll need this many here either. And obviously mine are not well spaced. And we'll tick off a few above and below the x-axis. Okay. Now, first thing we talked about, not a bad idea to start. Okay? What we're trying to do is sketch the graph of the function. Let's look at end behavior. That was the first thing we talked about in this section. What is happening in the long run? Very large x's, either very large positive x or very large negative x. Okay? Well, what you look at is the leading term, the term with the maximum exponent. That's going to govern what happens in the long run. It does some things, but not too much in the short term, but it does big time in the long term. Well, the two things we look at. Number one, the even or oddness of the exponent. This is even. That means in the long run, the function is either going up and up or down and down. Okay? What determines which direction it's going is the sign of the leading coefficient. And the leading coefficient is a 3, a positive 3. That means it's going on the up and up. So it's going up here, and it's going up here. Where it is, we don't know. But in the long run, this function is going up and up. Okay? Now, so that gives us our end behavior. Okay? Based on the leading term. What the power of the exponent is. That happens to be even, so they're both going in the same direction, and with a positive coefficient here, they've both got to be going positive. All right, that's done. Next thing we do is basically factor, okay? And the greatest common factor here is x cubed. And when you pull out an x cubed, you're left with a 3x from the first term minus a 4 from the second term. Okay? Now, what we do with the, oh, here comes Jakiria. So hold on just a minute. I've got her let it into the class. And I need the marker on my roll book if I can reach that far. Good deal. Okay. So for Jakaria and anyone else who came in recently, we're in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree. 2.1 was Quadratic Functions. Now we're doing higher degree from that. And the my Wacom board decided to erase my parentheses there, so let me put it back in. Okay. So we've first, oh, here comes Ashford. So Ashford's now coming into the class, and I've got him on the roll book. Okay, top of the alphabet is now doing pretty well. Middle of the alphabet's not too bad. The bottom part, Anaya's almost holding it down by herself. Okay, so hopefully some more will be coming in later. Okay. So for Ashford and others who just got here, we're in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree, whereas 2.1 had been Quadratic Functions, Degree 2. These are higher degree. Example 4 on page 128 is where we're starting. Sketch the graph of this function, x 3x fourth minus 4x cubed. First thing we did was look at end behavior. Look at the leading term, the one with the highest exponent there. That governs what happens to this polynomial function in the long run. When x gets very, very, very large negative numbers, and I'm going to choose one not that big, like 10, negative 10. Negative 10 to the fourth power is 10,000 times 3 would be 30,000. So, yep, that's going up, really high up. Okay, if you choose x to the right, like positive 10, that would be 10,000 times 3 is 30,000. So yeah, both of those are going upward. That's how I like to do it. You can follow the rules like I said before. Okay, next thing we did was factor that polynomial. And the obvious factor, if I could get the pen to show up, here it is a factor of x cubed. Common factor of x cubed, factor that out, and that leaves you 3x minus 4. Okay, now why did we do that? We're going to set that equal to 0. Now what does setting that equal to 0 do for us? That gives you, if the f of x is 0, that's the y is 0, and y is 0 when you're neither up or down from the x-axis. You're somewhere on the x-axis. So when you set that equal to 0, we see that either x cubed is equal to 0 or 3x minus 4 is equal to 0. Now x cubed equals 0. Basically that's a triple 0 at x equals 0. So there's a 0, there's a 0, and there's a 0. Okay, 3 of them right there. That's the same point. Okay. Set this equal to 0, add 4 to both sides. What we're doing is solving for x here. These add to 0, and you get 3x is equal to 4. Divide both sides by 3, and that gives us x equal 4/3. X equal 4/3, that's 1 1/3. So that's somewhere right about there. Okay, if I could get the pen to draw. Okay, there's our second 0. That's all the zeros of this polynomial function. We can almost fill in the gaps here. Okay, here's the one thing that we will do that's going to be a little unusual. This triple 0 at 0. Now you know the function is heading north here on this side, so this is going very, very far north because it's going to positive. As x gets negative, this gets very, 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 very positive. We saw that. Okay, now because that's a triple root here, we know we've got to cross the x-axis here, but because of the triple root, we're going to hang around the x-axis for a little bit here. Okay, and here it's got to be heading up here because of the end behavior here. So it's heading up here, heading up here. So therefore, the function in between is somewhere in there. Now, I probably didn't draw it too well. Definitely didn't draw it too well. So what we do now is get some test points. Keep them easy, simple. We have two functions here, two values here, an x equals 0 there and an x equals 0 here at 4/3. At 0 and at 4/3. Pick something to the left of that 0, like -1. So let's take our function f at -1. Now you can either use the original function or you can use your factored form. I don't think it really matters here, so let's just use the original. That would be 3 times a -1 to the 4th power minus 4 times a -1 to the 3rd power. Okay? Well, -1 to the 4th power is 1. -1 times -1 is +1 times another -1 is -1 times another -1 is +1 again. So this will be a 3 right there. Okay? Now, minus 4 times, now -1 to the 3rd power, like I just said, -1 to the 1st power is -1, -1 to the 2nd power is +1, and -1 to the 3rd power back at -1. So you have a -4 times a -1, and that would be 3 plus 4, because -4 times -1 is +4. 7. Okay, so let's go up 1, 2, 3, 4, 5, 6, 7. Barely got in there. Okay, so here's the next value. So this is going up even sharper than I indicated before. But it comes down here to the 0 and hangs around just a little bit, like a cubic function does, and then heads south. Okay, well, let's pick another point, something in between x equals 0 and x equal 4/3. Well, looks like a good candidate there would be x equal 1. So let's do that. F of 1. That's pretty simple. 3 times 1 cubed, 1 to the 4th, minus 4 times 1 cubed. Just plugging in. Okay? Now here's the beauty of plugging in 1. My favorite is plugging in 0. That's really easy to do. Second favorite is plugging in 1, because all you will wind up with is your coefficient. Okay? This gives you 3, because 1 to the 4th power is still 1. 1 to the 3rd power is still 1. So you have 4 minus 3, 3 minus 4, which is minus 1. So this has, at 1, you're down here at minus 1. Okay, if I could get it to draw. So my graph is not too far off, and then it goes here. Now, if you really want to try, pick a point to the right of 4/3. Well, closest point there, easiest one, would be 2. So let's do f of 2. Now, just like we did before, plug it in, plug it in. Okay, 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. Okay, now 3 times, what's 2 to the 4th power? 2 to the 1st power is 2, 2 to the 2nd power is 4, 2 to the 3rd power is 8, you multiply by 2 each time, 2 to the 4th power is 16. Okay, minus 4 times, and we just said 2 to the 3rd power was 8. So what do we have here? 3 times 16 is 48 minus 32. That's going to be 16. Way off scale, okay? So before you ever get to this, you're way off scale here. So this thing's going up fast, very, very fast, never makes it to 2, okay? So our graph is, my graph is sort of ugly, but I'll show you how it looks in the book. And you can almost tell that it's similar, okay? There it is right there. So you see it's not too far off from what the book says. Mine's a lot messier. Okay, now if you blow that up, I think that's what you see there. You see how it hangs around 0 there, but flies right past 0 there. It's going up really, really quickly. Now, what we said before, this 0 has a multiplicity of 3. That's why it hangs around there a little bit longer. This one has a multiplicity of 1. They usually don't say that, but it is. That means it just flies right up past it. It is at 4/3, 1 1/3, and it just goes straight through it. This is an odd multiplicity, so it does go through it, but it hangs around there a little bit longer. Okay, so that's the reason that the graph looks the way it does. Now, they also show those test points down here, and you see that is again pretty close to what we've got on our graph. They did a test point at 2. Of course, they had the point at 1 at 4/3, the 0 there. Then they had one at 1, -1, and for some reason they threw another one in there, I think, and then they had one at 0. Now it looks like somebody else is coming in. Tamia is here. Let me get her marked present. So Tamia is here. Good deal. All right, we're now up to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Lucky 13. Let's make sure that's what we've got here. Yep, 13 plus me. Okay. And Tamia, we're on in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree. 2.1 have been quadratic functions. Degree 2, these are higher degrees, and we just have finished Example 4 on page 128. And as always, I believe as always, they have their, right after every example, they have a checkpoint. So please do the checkpoints. Okay, any questions on those before we move to example 5? Okay, I'm going to clear the drawing I have, and you're probably very thankful for that. And let's do example 5. Okay, it says sketch the graph of this function. Oh boy, where's my pen now? Look at that. This is such a pain in the neck. Okay, let's see. There's my pen. Here's the function, f of x, it looks like a t, but that's an f, is equal to, oh boy, what a fun one this time, negative 9 halves x plus 6x squared minus 2x cubed. Okay, what a function. Okay, this is on page 129, example 5. Now, don't let those fractions scare you. They're just numbers. Okay, and the fact they have them in descending or increasing, ascending order of the powers, don't let that bother you. You can change that. Okay, what we're interested in, though, to begin with, is, and all it says to do is sketch the graph. So the first place to go, as we did before, would be to determine your end behavior. So let's get the graph drawn here. Somewhat of a vertical line there, somewhat of a horizontal line there, and tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We certainly aren't going to use that many. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere over there at 10, and going up 1, 2, 3, 4, 5, 6, 7, and down negative 1, 2, 3, 4, 5, 6, 7. Or maybe even get an 8 down there. Okay, where do we look for our first? Our end behavior. What's your leading term? Now, leading term doesn't mean the first term. It's the one with the greatest exponent, and that happens to be this one. There's your leading term, negative 2x cubed. Well, let's first look at the exponent. It's an odd exponent, meaning one of these is going up, one of them's going down. When you go positive or negative, one's going up, one's going down. If it's odd, they're going in the same direction, up and down and down. If it's even, they're going in the same direction, up and down, down and down. But if it's odd, one's going up, one's going down. What we have to figure out is which is going where. That's where we look at the sign of your coefficient. Oh, and here comes Terrell. Okay, let me get Terrell in here, and let me get him marked on the roll. All right, top part of the alphabet is really strong now. Middle part's pretty good. Bottom part still kind of shaky there. Poor old Brianna, Tamia, and Anaya are holding it down all by themselves. Okay, so Terrell, if you're here where you can hear me now, we're in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of Higher Degree, because 2.1 had been Quadratic Functions, Degree 2, and then we're on page 129 and doing example 5. Just have started drawing example 5. There's a function, really bizarre function here, okay, and we've identified the leading term. It's not the one that's first necessarily, it's the one with the highest exponent. That has an exponent of 1, 2, and 3, so we go with the 3, leading term. Since it's an odd exponent, that means you're going up on one side, down on the other side when you're doing your end behavior, positive and negative numbers. What helps determine which way you're going where is the sign of that coefficient. That's a negative. And here's what I like to do. I like to use an x that's sort of big but not too awfully big, like negative 10. Okay, x equal negative 10 is going to be way out this way somewhere. Okay, if you multiply negative 10, if you cube negative 10, you're going to get a negative 1,000. Okay, multiply that by negative 2, you get a positive 2,000. So I would say that's on its way up. Definitely on its way up there. That would indicate this must be on its way down here, but let's check and see here too. Pick a fairly large positive number like 10. 10 cubed is 1,000. Negative 2 times 1,000 is negative 2. Yep, that's on its way down. Okay, way down. Okay, so there's our end behavior. We've got that. What do we do next? Well, the next step is to find the zeros of the function. And what's the zeros of the function? It's where the function is equal to 0. So set that equals to 0. Now once you do that, you don't have to worry about the 2 in the denominator anymore. You can multiply everything on both sides of the equation by a 2. Okay? And that would give you a minus 9x plus 12x squared and minus 4x cubed. And here comes Ivan. Let me get Ivan here into the class and mark him that he's in the class. And the top part of the alphabet is getting even stronger here. Okay? We've got the top 1, 2, 3, 4, 5, 6, 7, 8, 9 students here on the top. Okay? So, way to go. Keep them coming. So Ivan, we're in Chapter 2, Polynomial Rational Functions, Section 2.2, Polynomial Functions of Higher Degree, and we're doing example 5 on page 129 right now. Okay? What we did first was identify our leading term, which isn't necessarily the first term. I can't get my pen to show. There it is. Okay. It's the term with the highest exponent, and that was the cubic exponent. Okay, we found out from that because it's a cube, an odd number, one of these is going up, one's going down. Because that leading coefficient is negative, that means when x is negative, your y is going positive. When x is positive, the y is going negative. So that gave us our end behavior. Next thing we wanted to do was find our zeros for the function. And how do we get those? Set the function equal to 0. And once you set it equal to 0, you can get rid of that denominator. Multiply everything on both sides of that equation by a 2. So that gives you negative 9x plus 12x squared minus 4x cubed equals 0. Okay. Now, I wanted to do something else, but I was afraid it'd be too confusing. What I'm going to do now is set this in the right order, and I don't like having a negative coefficient for my leading term. So I'm going to multiply everything by a minus 1 as well. So I could have multiplied by minus 2 if I had chosen to, but I'm going to multiply by minus 1 and rearrange the order. So what we have is 4x cubed minus 12x squared plus 9x is equal to 0. Now that's legal because it's an equation now. It's no longer just a function, it's an equation. You can multiply and divide by anything you want to, except don't multiply or divide by 0. That wipes out all meaning. Now, looking at that one now, I'm beginning to suspect well, first, the easiest thing to do is factor out an x. Okay? Aren't any other common factors except the x. So let's factor out the x. X times 4x squared minus 12x plus 9, and that's still equal to 0. Now, I know one root here is going to be x equals 0. Pretty obvious. So we know 0, 0 is going to be one of the zeros of that function. Okay. Now let's see, can we factor that any further? Now what's sort of a good dead giveaway here is the fact that's a perfect square, that's a perfect square. They're both positive. So let's see if that would be a 2x, and the middle term is negative, so make it 2x minus 3 and give us another 2x minus 3. Now that's just a guess. I think it's a educated guess, a good guess, but let's make sure that works. For it, 2x times 2x is 4x squared, sure enough. 2x times a minus 3 is minus 6x, minus 6x, sure enough, that's minus 12x, and minus 3 times minus 3 is plus 9. So yep, x equals 0 is a 0. I plug that in, and then the next one is 2x minus 3 equals 0. But that's a double root, okay? Well, what is that going to be? Add 3 to both sides, and you get 2x, because these add to 0, is equal to 3. So x is equal to, divide both sides by 2, and that gives you x is equal to, because the 2's divide away, x is equal to 3/2. 3/2 is 1 1/2. So there's your other 0. But that now, folks, is a double 0 because it's 2x minus 3 times 2x minus 3. What that means for us is your function doesn't cross the x-axis, it kisses the x-axis and heads back. Now, since we know ultimately the end behavior is going down, that means it's going to go like this. Now, I probably haven't drawn it well, but like that. Which means, of course, also, it's got to turn around back up and go through this one. That's a single zero, so that's heading north really quickly. So that's how I'm guessing the function looks without any test points. So let's do some test points, test intervals. Let's do something to the left of our first zero, like -1. Now this one's a real pain in the neck, so let's see if we can do this one, okay? So f of -1 is going to be, go back to your original function here, that would be minus 9/2. Yeah, get out of there. I don't know if you can see that, but I just got a black thing that showed up on the screen that blocked my writing. -9/2 times a -1, because there it goes again. Okay. We're just plugging in a -1 everywhere you see an x. Okay, plus 6 times a -1 squared, minus 2 times a -1 cubed. Okay. Well, minus 9/2 times a -1 is a positive 9/2. Now, plus 6 times a -1 squared. Well, -1 squared is positive 1, so that's 6. And then we have a minus times a minus, because -1 cubed is -1, and minus 2 times -1 is plus 2. I would say that's positive, okay? This is 4.5, and 6 would be 10.5, and 2 would be 12.5. That's heading north really, really fast. So at -1 here, you're way, way above this. So I'm not even going up fast enough there, okay? Now let's pick another point in between this 0 and that 0. Oh, here comes Diana. Let me get Diana in the room and on the roll book. Okay, Diana's here. That gives us 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Should be 16 students now. Let's see what we've got. Yep, 16 students. And I don't think anyone else is in the waiting room. Let me just make sure. Nope. So, all right. So Diana, we're on in Chapter 2, Polynomial and Rational Functions, Section 2.2, Polynomial Functions of higher degree. 2.1 had been Polynomial Functions of the second degree, which is quadratic functions. Now we're doing higher degrees. We're on page 129, example 5, and we're pretty well along the way in example 5. So you'll need to go back and listen to YouTube video to pick up things that you may have missed so far. What we have done so far is found out the end behavior for this function, and for some reason the pen, that's why I'm holding it backwards, that's why. Okay, the end behavior is determined by the leading term, which means it's going up to the left, down to the right. Okay, go back and listen to us. Then we did the zeros of the function, found out there was x equals 0 and x equal 3/2. So we put our two zeros in. Now we're doing our test point, so we chose something to the left of the first 0, a -1, and found out that was, what was it, 12.5? Okay, so when x is -1, we're way up there, so that our end behavior looked like it was right. Okay, now we're going to do a number in between the two zeros. Well, x equal 1 looks like a good one. So f of 1. Now, if you remember what I said a little bit earlier, is that's just your coefficients. Just add them together. That would be a -9/2 times 1 is -9/2, plus 6 times 1 is 6, minus 2 times 1, because 1 cubed is 1, That's minus 2. So this is minus 4.5, and another minus 2 is minus 6.5, and then a plus 6, that would be a minus 1/2. So obviously I drew mine a bit too steep. Well, no, maybe not. Well, I did do it, yeah. So it's about negative 1/2. So I wasn't far off. It does have a minimum somewhere there, comes up, kisses there, and goes back down. Well, let's see where it goes back down. Let's do something to the right of that last 0. That would be maybe 2. So let's do f of 2. And again, just plugging in here, that would be a minus 9/2 times 2 plus 6 times 2 squared minus 2 times 2 cubed. This will be, the 2's divide out, and this will be a minus 9, I don't know what that noise is, plus 2 squared is 4 times 6 is 24, minus 2 cubed is 8 times 2 is 16. That's a minus 16. So minus 29 and minus 16 would be a minus 25 plus 24. That's going to be a minus 1. And that wasn't too far off right there. But then it keeps going south really, really quickly. Okay, so we've confirmed that's about how the graph looks. Okay, so let's see how the book did it. Was someone trying to get in touch with me? Is that a chat? Are you talking with each other? If you're trying to get in touch with me, go on and spew it out there, because if I open the chat, everybody will see it anyway. Okay, so here is that graph. If I can get, oh, there it is. Okay, my fingers are covering it. And sure enough, we are not too far off from what their graph is. End behavior first, that's what they show in that part, and then filling in the blanks, your zeros there, and then picking some test points on any side, all sides of the zeros. Does that make sense? And as with every example, there is a checkpoint. So please do the checkpoints as soon as you can outside of class. All right, let's go back to our PowerPoints now. Any questions before we leave that graph? Okay, let's go back to the PowerPoints, and we'll resume the slideshow with the intermediate value theorem. Okay, pretty impressive sounding name there, right? This is on page 130. Here's what it says. The intermediate value theorem implies that if you know 2 points, x equal a, of course your y would equal f of a. That's what your y value is, f of a. You know another point, x equal b, the y value would be f of b. So these are 2 points on the graph of a polynomial function. Now remember 2 characteristics of a polynomial function. The graph is smooth and continuous. Okay? That continuous part is really the important part here. These are 2 points on the graph of a polynomial function such that f of a and f of b are not the same values. Okay? F of a could be higher than f of b, or f of b could be higher than f of a. They just can't be the same value. Okay? Now, then for any number d, whoa, okay, where's that? Between f of a and f of b. So here's your f of a, here's your f of b. So any d in between f of a and f of b, okay? There must be some number c on the x-axis between a and b such that f of c is equal to d. Boy, a lot of letters there, aren't there? Blah, 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 blah. Okay? Now, here's how they showed theirs. Here is your a value. There's your f of a. You plug in whatever your function a is, f is, you plug in a for the x and see what the y turns out to be, f of a. Do the same thing for b over here, and you find out the y is somewhere up here. This is an increasing function. in that interval anyway. Okay, well, pick some number D in between f of A and f of B, then there's got to be some number C that f of C is equal to D. Alphabet soup, right? Okay, that's all intermediate value theorem is saying. If you got two different y values on a polynomial function, then for any value in between those y values, there has to be an x value in between A and B that gives you that value for y. F of C is equal to D. That's it. Okay, the reason it's true, because polynomial functions are smooth and continuous, mostly the fact that they're continuous. Okay, now here's it stated a little differently. Let A and B be any real numbers such that A is less than B. Okay, if f is a polynomial function, and that's what we're dealing with now, such that f of A is not the same as f of B, then in the interval between A and B on your x-axis, f takes on every value between f of A and f of B. Okay, so not only is it just one value, it's any value. So between f of A and f of B for a polynomial function, every value in between there is accounted for. Every one. For whatever D you choose in between f of A and f of B, you're going to find some C that gives you that f of D. That's your intermediate value theorem. So that helps you locate real zeros in the following way. If you can find the value f of x, or x equal A, at which a polynomial function, say, is positive, and then you find another value, x equal B, for which it is negative, that means somewhere in between that, if it's positive here, negative here, you've got to have a zero somewhere in between that. Yes. Okay. Okay. I'll be watching for you, so don't give up on me. I'll be watching to let you in. All right. Yeah. Okay. Now, so that way, if you can find the place, a value, x equal A, for which, say, a polynomial function is either positive or negative, and then another value, x equal B, for which it's the opposite, you know there has to be at least one zero, real zero, in between those two values. You may have more than one, okay? That's okay too, but you've got to have at least one. Now, finding them, that's another issue, okay? And you'll have to deal with that. So let's see how we're going to do this. Here's an example for the function f of x equal x cubed plus x squared plus 1, okay? They claim that that's negative when x equal negative 2. Well, let's see if that's true, okay? Let's see if that's true. F of negative 2 would be negative 2 cubed plus negative 2 squared plus 1. Well, negative 2 cubed is negative 8. Negative 2 squared is plus 4. And then plus 1 is plus 1. So this is going to be minus 8 plus 5. That would be minus 3. So sure enough, that is negative when x equal negative 2. Well, let's come up 1 to where x is negative 1. So f of negative 1 would be negative 1 cubed plus a negative 1 squared plus 1. Well, negative 1 cubed, sure enough, is negative 1 plus negative 1 squared is just 1 plus 1. Well, what's that equal to? Minus 1 plus 1 is 0. This is equal to 1. Guess what, team? F at negative 2 was a negative number. F at negative 1 was a positive number. Somewhere in between x equal negative 2 and x equal negative 1. See, here's the negative 3 down here. Here's a positive 1 up here. There has to be a 0. how do you find it? Okay, well, there are several techniques. Basically, what I would do is pick a number in between -1 and -2, like -1.5. Now, I'm not going to do this in my head anymore because decimals are harder to do, so I'm going to get my calculator. I can unplug it because it's charged now. It's my phone, by the way. Okay, and get it over to calculator mode. Remember when you used to use phones to call people? Okay, this is not good. It's not loading my calculator. I wonder if our internet signal is weak. So I'm not going to use the calculator. So I'm going to put that aside, and I guess I'm going to have to do this by hand. Okay, so what is f of -1.5? That would be -1.5 cubed plus a -1.5 squared plus 1. Okay, now this is a pain. Okay, -1.5 cubed, let's see if the calculator's opened up yet. Says unable to install my calculator, which I found hard to believe. This is such a pain in the neck. Okay. I'm going to try something. I guess I hadn't cleared my storage lately, but I don't have much there. Now let's see if we can do that. Still not doing. This is my wife's old phone, and it has a lot of stuff on it that she had on it. I don't even know how to go about messing with that. Okay, so let's do, well, I'm not going to take the time to do it. It would just take too long. -1.5 squared. Let's do that one first. That one is fairly easy. That is, where in the world? Oh, wait, here's Brianna coming back. So, I think I already had her present. Make sure. Yes, so Brianna's back. Good deal. Okay, -1.5 squared is 2.25. I just happen to know that. Okay, if you multiply that by another 1.5, I hope I'm right on that. Okay, that would be a 25, a 2, a 1, and then a 1, 2, a 2, 2, 5. Multiply those together, add those together, you get a 3.375. And that's going to be negative because that was a negative cubed is negative. So here we have a -3.375, a plus 2.25, and then a plus 1. Okay, I still wish I had my calculator. Okay, but this comes up to be 3.25 minus a 3.375. That's just going to be slightly negative. So at -1.5, if I could get my pen to show up here, it's going to be slightly negative. So now we know, get out of there. Now we know that it's something in between -1.5 and -1 because it's positive here and negative there. So you keep narrowing it down. Plug in, say, rather than -1.5, I would say -1.4 because that looks pretty close. Keep doing that until you get something above, and then you basically sandwich it in. Okay, it's somewhere between -2 and -1. We know it's between -1.5 and -1, so I would have guessed -1.4. Okay, but anyway, I did more than they wanted you to do there. By continuing this line of reasoning, you can approximate any real zero of a polynomial function to any desired accuracy. It will take a while, but you can do it. So this concept is further demonstrated in example 6, and here's example 6, top of page 131. Use the intermediate value theorem to approximate the real zero of f of x equal x cubed, if I get this, minus x squared plus 1. So here's where I'm going to start. I'm going to start at the easiest thing possible, f of 0. Okay, f of 0 would be 0 plus minus 0, which is still 0, plus 1. So that would be 1. Okay, now I think our greatest bet here is to go negative. Okay, because that was positive. So let's do f of -1. That would be a -1 cubed minus a -1 squared plus 1. Okay, just plugging in. Okay, this will be, if I could get my pen to show back up, where on the world, there it is. Okay, this will be -1 cubed is -1. -1 squared is +1, but then when you negate it, that becomes a -1, and then you have a plus 1. Hey, guess what? Those add to 0, so now we have a plus here at 0, a negative here at -1. So our real zero must be between 0 and -1. So let's try f of -0.5. Let's just pick something directly in between those. So this will be -0.5 cubed minus a -0.5 squared plus 1. Okay, now I don't know if you know, let me see if my calculator's back. I doubt if it is. Let me see. Nope, it's still trying to load my calculator. This is a real pain in the neck. Okay, now I could also, and maybe we should do it this way, somewhere down here, oh, I can't get to it easily here. I was going to say you have a calculator mode on your computer too, but I would have to get that. So I'm just going to have to go by the seat of my pants here. Okay, -0.5, if I can find, there it is, -0.5 cubed, we know is going to be negative because negative cubed to the odd power is negative. Well, 0.5 times 0.5 is 0.25, right? Times another 0.5 is -0.125. Okay, minus, and this will be a positive 0.25, my pen would write, plus 1. Okay, well that's going to be -0.375 plus 1. So that's going to be positive 0.625, I believe. Okay, so now we know that it's in between -1 and -0.5 because this one's negative, that one's positive. So pick something in between those two. and I don't know where to pick, what to pick. This is further away. This is a -1. This is a positive 0.625. So I think it's going to be something closer to 0.5 than it is -0.5 than -1. So let's do -0.7. So let's do f of -0.7. Now this is a real pain in the neck because these are not pretty numbers. I don't know what -7 cubed is. I'm probably going to get in trouble for doing this, but I'm going to... Okay. Oh, you're kidding me. Okay. Okay. Let's see if that will work now. Oh, yuck. What a pain in the neck. I'm not going to mess with that anymore. But this is the process. Try that one. If you got a calculator, do it. That would be -0.7 cubed. That's going to be something, a negative number. And then this is another negative number plus a 1. Whoever wins there, the plus or the minus, then you go to the next one. So let's just see how they do it. Okay, sorry about that. My calculator screwed up on me this morning. Let's see. What I need to do is clear my screen here, and let's see what they did. Begin by computing a few functional values. They did f of -2 was -11. That was way off. -1 was -1. That's better, but you know it's nothing in between those two. At 0 it was +1. There you have it. The 0 has between those two. Don't even mess with this one. Okay, has to be between 0 and -1. Okay, so they chose, because f of -1 was negative, f of 0 is positive. You can apply the intermediate value theorem and conclude the function has a real 0 somewhere in between x equals -1 and x equals 0. They chose to pinpoint the 0 more closely, divide the interval between -1 and 0 into tenths, and evaluate the function at each point. Okay, well, they knew the answer. They went to -0.8, found out that was negative there. -0.7 was positive. If we had done the math, we would have found that to be true. Okay, so they know it's somewhere in between -0.8 and -0.7. So they just show it here. Okay, they stopped right there and said it's something in between -0.8 and -0.7. It had to be, because it was negative on this side, positive on that side, somewhere in between. We don't know exactly the value, but you can narrow it down like -0.75 and see whether that's positive or negative, and then go in between the next two and the next two and the next two. Okay. For a more accurate approximation, compute function values between f of -0.8 and f of -0.7. Apply the intermediate value theorem again and again and again. By continuing the process, you can approximate the 0 to any desired accuracy. You may not ever get the exact value, but you can get as close as you want to get. And that's the end of the slideshow. Okay, so there is a checkpoint after example 6. Please do the checkpoint. There's a summary right at the end of that. Please do the summary. Let's see, how much time do we have? Oh, we got a few minutes. Let's do our vocabulary. Okay, These are fill in the blanks, and there's 8 of them, lots of blanks here. The graph of a polynomial function is blank, which means the graph has no breaks, holes, or gaps. What does it mean when there's no holes, no gaps, no breaks? That function is C word, continuous. Okay? Number 2, the blank 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 is used to determine the left-hand and right-hand behavior of the graph of the polynomial function. Now the book called it one thing, I called it something else. What is that? The leading term test. The book called it leading coefficient test. I call it the leading term test. It's a bit more precise. Okay? Number 3, a polynomial function of degree n has at most how many real zeros? At most n. Okay? If it's an nth degree polynomial, you can have up to n real zeros. And how many turning points? N minus 1. Always one less than the number of your exponent. Okay? Now, number 4. When x is equal to a is a zero of a polynomial function, the 3 statements below are true. You just have to fill in the blank to make them true. X equal a is a blank of the polynomial equation f of x equals 0. Okay? Now the first one said when x equals 0 is a zero of the polynomial function, the following statements is true. X equal a is a blank of the polynomial equation f of x equals 0. That's a solution. B, blank is a factor of the polynomial equation. If x equals 0, x equal a is a root of the polynomial function, what would be the factor of that? X minus a. Subtract a from both sides of the equation. X equal a, subtract an a, and you get x minus a equals 0. That would be a factor. The C one, a comma 0 is an blank of the here's Weston. He must have gotten kicked out and come back in. Okay, I already had him here. Yes, he is. So he's here for the last few minutes here. Okay, we got 3 minutes to go. All right. So a comma 0 is an x-intercept of the graph of f. That's where it crosses the x-axis. Number 5. When a real zero, x equal a, of a polynomial function f, is of even multiplicity, the graph of f blanks the x-axis at x equal a. It touches it, it does not cross it. So that touches it. And when it is of odd multiplicity, even including 1, the graph of f crosses the x-axis at x equal a. So it touches it if it's an even multiplicity, it crosses it if it's an odd multiplicity. Number 6, a factor x minus a to the kth power, where k is greater than 1, yields a blank blank x equal a of blank k. Okay, boy, a lot of blanks there. Okay, that yields a repeated root of x equal a, and it's repeated, has a multiplicity of k. So the last blank is multiplicity k. Number 7, a polynomial function is written in blank form when the terms are written in descending orders of the power from exponents from left to right. It's called standard form. Remember we did one which is a minus 9/2 x plus, and ultimately we got it into standard form. Okay. Number 8. The blank blank theorem states that if f is a polynomial function such that f of a is not equal to f of b, then in the interval between a and b, f takes on every value between f of a and f of b. The blank blank theorem. The last thing we did. Intermediate value theorem. Okay, sorry I gave too many answers, but we're running out of time. We've got 1 minute left. So here are the homework exercises. Try to do all the 9 through 14. Now only the odds are going to have answers in the back of the book and at calcchat.com, but I think you can match the those 6 graphs with 9 through 14 functions. Okay? Then do any of the odds, 15 or 17. They're both at CalcChat. 17's at CalcView. Any of the odds, 19 to 27, they're all at CalcChat. 21's at CalcView. Either 29 or 31, both at CalcChat. Any of the odds, 33 to 47, all at CalcChat. 43's at CalcView. Any of the odds, 49 to 51, either 49 or 51, both at CalcChat. 53 to 61, all at CalcChat. 59's at CalcView. Any of the odds, 63 to 69, they're all at CalcChat. 67's at CalcView. Any of the odds, 71 through 83, they're all at CalcChat. 73's at CalcView. 85 or 87, they're both at CalcChat. Do they have enough problems here? I think they do. Any of the odds, 89, either 89 or 91, they're both at CalcChat. 89's at CalcView. Any of the odds, 93 through 97, they should all be at CalcChat. Then any of the true false, any of the odds 99, either 99 or 101, they sure do have enough, don't they? They should both be at CalcChat. And then 103 through 107, they should both be at CalcChat. We'll begin next time with 2.3. Any questions? All right. So take care, folks. Have a good, safe weekend. I know it looks like. Yes. What's your question? I think it's the same as the last day of class. It's that for this class, that's a Thursday. I think the first Thursday in December, I believe it is, because that's the last day of class. Then next week is the final exams. Okay, the second, and I think our final is probably on that Tuesday of that second week in December. And that's when your final exam will be due. I'll give it to you the Thursday before that last day of class, and you have until the next Tuesday to get it in. You can take a little longer if you need to, but I don't think that's quite as rigorous as it used to be when everybody was on campus, because they will get everything finished up. So I'll give you the final that last Thursday, the first Thursday in December, and try to get it into me by the following Tuesday, or as soon as you can. Does that answer your question? Okay, good deal. All right, any others? Okay, folks, be safe. Be careful this weekend. The virus is still out there big time. The numbers are climbing like crazy. I'm going to stop sharing right now. Please be careful. Be safe. We'll see you on Tuesday, okay? And maybe see a couple of you before then. Okay. Take care. We'll see you Tuesday. Bye-bye. Ending the meeting for everybody.